Welcome to sysadmin. Today, we're going to get right down to the bedrock of digital communication. We're talking about how computers actually represent and transmit data. Getting a solid grasp on this is absolutely crucial for any IT pro. It's the foundation for pretty much everything we do, from troubleshooting a flaky network connection to configuring a brand new server. So, let's dive in.
So think about this for a second. Every time you type a letter, send an email, or even just wiggle your mouse, have you ever really stopped to wonder what is actually happening inside that machine? How does this hunk of metal and plastic, this collection of silicon and copper, have any idea what you're trying to tell it? Well, the answer is actually surprisingly pretty simple. Everything, and I mean everything, gets translated into one universal language that the computer can understand. It doesn't matter if it's text, numbers, sounds, pictures, you name it. It all gets broken down into these long, long strings of just two numbers, ones and zeros. And this universal language, we call it binary. Okay, so if it's all just ones and zeros, how in the world does a computer know the difference between, say, the letter A and the number 65? They look totally different to us. The secret, it turns out, is all about how we group these ones and zeros together to create a sort of digital alphabet. Right, so let's start with the smallest possible piece, the bit. It's short for binary digit, and you can just think of it as a tiny light switch. It can be on, which we call a 1, or it can be off, which we call a 0. Now, one bit by itself, not super useful, right? But when you start stringing them together, that's when the magic happens. You can start representing way more complex stuff. Now, let's be honest. Staring at a giant wall of ones and zeros is, well, it's a nightmare for us humans. So to make our lives easier, we use a kind of shorthand called hexadecimal, or just hex. It's pretty clever, actually. It just groups 4 bits together into a single character, using the numbers 0 through 9 and then the letters A through F. The computer doesn't see this, it's still all binary underneath. But for us, for programmers and sysadmins trying to read raw data from a network packet or a memory dump, oh, it's a lifesaver. All right, so we've got bits, and we know we can group them, but that's not enough. For my computer to have a meaningful conversation with your computer, they both need to be speaking the same language. They need to agree on what each group of bits actually means. We need a shared dictionary. And in the tech world, we call that a code set. And a code set is really just that. It's a standardized rulebook. It's a big chart that maps every character, every number, every symbol you can think of to its own unique pattern of bits. You can imagine the chaos without these standards, right? The letter A I send from my machine might show up as a smiley face or just total garbage on yours. So these code sets are the absolute key to making sure different systems can actually understand each other. And believe me, there have been a few of these dictionaries over the years. Way back, you had Baudot code, which only used 5 bits, perfectly fine for old-school telegraphs. Then IBM came along with their 8-bit EBCDIC for their big mainframe computers. But the one that really won out, the one you've probably heard of, is ASCII. That's the American Standard Code for Information Interchange. It uses 7 bits for the character itself, and it often tacked on an 8th bit, called a parity bit, for some really basic error checking. Super important stuff. Okay, so we've nailed down how data is represented. The next big question is, how do we actually move it? How does it get from point A to point B? We're talking about getting it from your computer to your printer, or from a server in New York to another one in Tokyo. You need a way to transmit it, right? Turns out there are 2 basic ways to get this done. Let's use a highway analogy. First, you've got parallel transmission. Think of this as an 8-lane superhighway, where 8 cars, or bits, can all drive side by side, all at the same time. Then you have serial transmission. This is more like a single-lane country road. All the cars have to get in line and follow each other, one after the other. And here's what that looks like in the real world. A parallel connection literally has multiple wires inside the cable, maybe 8 of them, and each wire carries 1 bit of your data at the exact same moment. But with a serial connection, it's totally different. You've got just 1 wire, 1 channel, sending that whole sequence of bits down the line one at a time. So what's the deal with parallel? Well, its big advantage is speed, but only over very short distances. It's fantastic for things happening inside your computer, or maybe for connecting an old printer that's sitting right on your desk. The downsides? First, it's expensive. All those extra wires add up. And second, if you try to send data too far, the bits can get out of sync. It's like some cars on our highway arriving a little earlier or later than others, and that just scrambles the whole message. And that is exactly why serial transmission is the king of modern networking. It's just so much simpler and cheaper, right? You only need one channel. And it's way, way more reliable over long distances because you don't have that synchronization nightmare. Honestly, it's the backbone of pretty much everything we use today, from your USB mouse to the entire global internet. But wait a minute. Sending everything down one single lane introduces a massive new problem. If all you see is this endless stream of ones and zeros flying by, how on earth does the device on the other end know where one character stops and the next one starts? This is the huge challenge of synchronization. And that's the bottom line. Without some kind of shared timing, a shared heartbeat between the sender and the receiver, all that data just turns into meaningless noise. The receiver has to know the exact moment to look at the wire to read each bit. And this whole process of getting everyone on the same rhythm, we call that clocking or framing. So how do we solve this? Well, in the most common form of serial communication, called asynchronous, we do something really smart. We wrap each and every character in its own little digital package, called a frame. Think of it like putting a letter in an envelope. It has a clear beginning and a clear end. First, you get a start bit. That's always a 0. Then you get the actual data bits, the character itself. You might get an optional parity bit for a quick error check, and then you get a stop bit, always a 1 to say, hey, we're done here. Let's actually walk through this. So imagine the line is just sitting there, quiet. Suddenly, that start bit comes along and it's like a shout. Hey, wake up, data's coming. The receiver then starts listening and reading the next few bits at a speed you've already agreed on. Finally, that stop bit arrives and the receiver knows the character is complete and it can get ready for the next one. This method is brilliant because it lets the receiver resync for every single character. It makes the whole system super reliable. Okay, I know what you might be thinking. This is all super low-level stuff. Do I really need to know this? And the answer is absolutely yes. Understanding these core concepts is so practical for any sysadmin. Let me tell you why this matters, because you are going to see this stuff out in the wild. For starters, if you've ever plugged that blue console cable into a router or a switch, you've had to manually set things like bits per second, data bits, stop bits. Sound familiar? That's what we've been talking about. When a network connection just dies, you're troubleshooting a problem at the physical layer, a serial transmission problem. This knowledge is what helps you truly understand why things like error checking are so critical. And it's what lets you look at a packet capture in Wireshark and actually make sense of the raw, low-level data you're seeing. It's not just theory, it's your job. All right, let's wrap this up and quickly recap the key takeaways. This really is the bedrock of all digital communication. First off, everything inside a computer is just binary, ones and zeros. That's it. Second, to give those ones and zeros meaning, we use standardized code sets like ASCII, which act as a universal dictionary. Third, we learn data can move 2 ways: parallel, which is fast but only for short distances, and serial, the reliable workhorse for modern networking. And finally, we saw how serial communication cleverly solves the timing problem by using frames with those all-important start and stop bits to make sure every single character is read perfectly. And that leaves us with one last big question to chew on. Everything we just talked about, those are basically the rules for sending a single letter across a wire. So how do we take these basic building blocks and scale them up to build something as mind-bogglingly fast and complex as the global internet, which is flinging terabytes of data across the planet every single second? Well, that's a story for another time. If you found this helpful, do us a favor and subscribe to System Administrator, and let's keep building your IT expertise together.